what an actual rational function is. So before we get started, does anyone have any questions on the homework from yesterday? Because I know the graphing part was something y'all were struggling with a little bit, so I wanted to make sure y'all had questions, ask them now. Lucas.
Can you review the one on the bottom right on page 32?
Yep, I can do that.
Like on the question.
Oh, like one of the graphing ones? Yeah. Okay. All right, so the graphing. So remember, both cube root and square root graphs have a very similar general form to that of vertex form of a quadratic. So that'll be y is equal to a cube root of x minus h plus k, where hk is known as your vertex. All right. So based off of that information, what do you guys think my vertex is? -4, -1. Good. So remember, since the minus is already in the formula, that means you flip the sign. The only one you don't flip is the k. The k stays as it is. Now, the y and x intercepts, you just had to go into Desmos and do. Okay, because they're not always pretty because we're dealing with square roots. So if it's not going to land on a perfect square or a perfect cube, it's going to be ugly. All right, so you just had to go into Desmos and do that. So I'm not going to bother with that right now, but then I'll talk about domain and range. All right, so domain and range. So we talked about this yesterday. What's always a domain range for a cubic? All real numbers for both. So remember, the only time you have to worry about the constricting domains and ranges is with square root functions. Cube roots, it's always going to be all real numbers. Now, the actual graphing part. So first off, you just want to go ahead and graph your vertex. So everything's going to be centered around it. And remember, that means you're going to have some over here and some points over here. It's not a negative function, so we know it's not going to be flipped. So remember what I said. All right. You want to go in terms of your perfect cubes. So in other words, you need to ask yourself, and remember the perfect cubes I said you should look for is -8, -1, 0, 1, and 8. These are the numbers that you want to show up under the radical if you plug that number or a number in for x. That's the number after you evaluate under the radical you should get under there. All right, so we already found the one for 0, which is -4. Because if you put under, -4 plus 4 is 0, cube root is 0, 0. And then -1 will give you that -1. All right. Now, for the others, what number could I put in for x that would give me -8? -12. So if I evaluate that, -12 plus 4, that's -8. What's the cube root of -8? Not 2, but -2. Remember, perfect cubes, they can be negative. All right. You will get a real number out of it. And what's -2 minus 1? -3. All right. What can I plug in for x to give me -1? So what can I plug in for x that when I evaluate what's under that radical gives me -1? Negative what? Not 4. 5. So -5. Because -5 plus 4 is -1. Cube root of -1 is what? Not 1. -1. So guys, if you take the cube root of a negative number, you're going to get a negative number. Always. So that would be negative 1. And what's negative 1 minus 1? Negative 2. What could I plug in for x that would give me 1 under the radical? Negative 3. All right. Cube root of 1 is 1. What's 1 minus 1? 0. And lo and behold, that's actually an x-intercept. So we can put that there. Lastly, what can I put on what can I plug in for x to give me 8 under the radical? Positive 4. So cube root of 8 is 2 minus 1, 1. All right, so now I'm going to graph all the points that I can. All right, so our graph isn't big enough. Well, if we just add one more, it would hit 12. All right, so let's do negative 12, negative 3, negative 5, negative 5, negative 2. We already graphed negative 4, 1, negative 3, 0, and then 4, 1. So our y-intercept is definitely going to be some weird number. So that one you definitely have to get into Desmos and then just round it. But this is right. All right, so here's how you would do it. So you can't use the square root key. You actually have to go to functions and then scroll all the way down until, do you guys see this radical with an n on it? If you click that, then you can input the 3. So it'd be 3 x plus 4 minus 1, and there it is. And since we're already here, let's get the y-intercept. So y-intercept is, let's say 0.59. Or you can just put everything that's on there because Desmos automatically rounds it for you. So let's say 0.5874. So the y-intercept is 0.5874. And obviously you don't need to graph that. Yes, ma'am.
Can you set x 0 and then solve for y? Find the y-intercept?
You could. You could. The only problem is that if you did that, so if I plug in 0 in for x, if you got like the exact y-intercept, like in terms of a radical, that's totally fine. And that's fine. That's completely fine. All right. But you didn't have to. So yeah, that's the other way you can find it. If you plug in 0 for x and evaluate it, this would just be y is equal to the cube root of 4 minus 1. And you would just left it like that.
I just did that for my calculator.
Yeah, and that's totally fine. This, if you put that in your calculator, you would get this. Or you would get like a rounded version of it. Yeah, that's totally fine too. Any other questions? So this one, yeah. Okay, this one was a little bit funky. All right. Because it was kind of hard to read a little bit. Now, bless you. Now, in terms of actually finding the vertex, they gave you 2 points. The hard part is trying to figure out which one is the vertex of the cubic. So the way you figure this out is that one of these has to be the vertex. All right. But remember, with a cubic graph, there's usually 3 different points. the 2 points on the outside of those 3 points within like the little kind of squiggle part, if you notice, they kind of are like right on the actual curve. All right. Where the middle almost looks like it's part of a linear function. So if I look at like where the squiggles are, the other squiggle will be right here. And these should be the same distance apart. So like they should have the same rate of change. So if you did rise over run, 2 over 1, 2 over 1. All right. So the vertex is actually 1, 4. So this is our vertex, and then the other point was just a point that they gave us so we can find the A value. All right. So remember, with a cubic function, we always start with a cube root of x minus h plus k. So 1, 4 is our hk. So what would our function be? And we take into account we haven't solved for a yet. So what would our kind of tentative or incomplete function be if we just plug in our vertex into here? Right. X minus 1 plus 4. Now, where the second point comes in is that that's what helps us solve for A. Who remembers what I said you have to do? Plug it in for x and y into the function, solve for A. So if I do that, I have y is equal to, not y, I have 2 is equal to A, bless you, cube root of 2 minus 1 plus 4. All right. Now, what's 2 minus 1? 1. So this will be the cube root of 1 plus 4. A is equal to 2. All right. What's the cube root of 1? 1. All right. So this would be 1 times A, or just A. This would be 2 is equal to A plus 4. What's our last step? Subtract the 4. So what's A equal to? Negative 2. Now, does it track that our A value should be negative based off of the way the graph looks? Yeah, because a normal positive cubic graph looks like this. This is a positive cubic graph. So a negative one is going in the opposite direction. So our final answer, if we take the A value, plug it back in, y should be equal to negative 2 cube root of x minus 1 plus 4. So I can understand the struggle with that one because it even took me a minute to figure out which one of those 2 points was the vertex. And that's just because the graph was just not the prettiest graph in the world. Any questions? Any other questions? Sure, we can do the square root one. All right, square roots are a little bit easier because the vertex is obvious. All right, so remember, square root is just y is equal to a square root of x minus h plus k. That's its general form. So it's pretty much the exact same as the cube root, except you just don't have the little 3 on top of the radical. So what's my vertex? -5, -2. So what would my tentative function B? So remember, we haven't solved for A yet. Good. Now, to get A, they didn't actually mark another point for us, but we can find one on the graph. So we want a pretty point. Okay? So remember what I said yesterday. A pretty point is when it clearly hits at a perfect intersection of a horizontal and vertical grid. All right? So what would be one pretty point on that graph? So there's two. You can either have done -1, 0, or you could have done 4, 1. Either one of those were pretty points. All right. I'm going to do -1, 0 just because it's smaller. So I'm going to plug in -1, 0 in for x and y. So this will be 0 is equal to a square root of -1 plus 5 minus 2. What's -1 plus 5? 4. So a square root of 4 minus 2. What's the square root of 4? 2. So 0 is equal to 2a, because we're multiplying that a to the square root of 4, so it's 2a minus 2. Add the 2 to the other side, you get 2 is equal to a, so what's a equal to? 1. So when we plug it back in, the a just kind of goes away because we're just multiplying by 1. So my final answer would be y is equal to the square root of x plus 5 minus 2. Any questions? Any other questions on graphs of square roots and cube roots? All right. So we're moving away from roots and we are going to go into rationals. All right. Now, when you get to math 3, you're going to have a huge unit on rational functions. Like it's a whole unit. But the ones that we're going to do are just the bare minimum basic ones. All right. When you get to math 3, you'll do the way more complicated ones. So having a decent foundation now will help you in the future. All right. Now, when you think of the word rational, what do you think of? What's a word that's kind of within the word rational?
Ratio.
Ratio. What's a ratio? It's a fraction. And that's exactly what a rational function is. It's a equation or function that is a fraction. Specifically, what makes it different than, say, just a linear function is that the variable is in the denominator. All right. So before we actually get into that, let's talk about something real quick. So rational functions are all about dividing by something. Usually we're dividing by x or x squared or something like that. So let's talk about, some basic division first. All right, so if there are 12 chocolates and 3 friends want to share them, how do they divide the chocolates? This is like a 3rd grade problem. All right, you obviously do 12 divided by 3, get 4. Now, what if the 12 chocolates were divided among 0 people? How much does each person get? Does that question even make sense? No, because if there's 0 people, how could you give someone chocolates? All right. So we can't share among 0 people. And just like how we can't share among 0 people, we can't divide by 0. What happens if you divide by 0? What's it technically? It's not 0. It says an error. So technically, if you divide by 0, you get what? What's the word? Nope. Say it again. I heard someone say it. Starts with a U. Undefined. So we can't divide by 0. It's undefined. Not even imaginary. Like it doesn't even exist. Like at all. All right. And here's another way to think about it. If 12 divided by 3 is 4, that means 4 times 3 is 12. So if we divided 12 by 0, that means whatever number we get means that if we multiply that number to 0, it will give us 12. But what's kind of the contradiction here? Especially right here. Say it again. Anything multiplied by 0 gives you 0. It's a contradiction. It doesn't work. Now, why is that important? It plays a huge role in rational functions, specifically when it comes to graphing them. All right. So what happens when you put 12 divided by 0 on your calculator? The vocabulary for this error is what? So put in your calculator real quick. Tell me the type of error you get. What does it say? Syntax. It's known as syntax. Now, you guys probably learned about this word in English. What does syntax typically mean in English? What is it? So in your English class, guys, I know you guys have talked about syntax. Well, this is 8th grade stuff. It's the structure or order of sentences. Same thing in math. It's the structure or order of what you put into your calculator. All right? So syntax is the structure or order of sentences in English. In math, it's how you set up an equation, a function, or expression, whatever. All right? So syntax error gives us a syntax error because your calculator knows you can't divide by 0. All right? Now, the other time that you saw an error on your calculator was when it said non-real. So like if we took the square root of -4, it would tell you non-real. All right? So what this means is that if you divide by 0, it's not even going to tell us, if we divide by 0, it's not even going to say it's an imaginary number. It just doesn't exist. That's why we say it's undefined. I bet you guys never really knew why we can't divide by 0, did you? When I was going through school, had no clue why we can't divide by 0. All I knew is that we couldn't. And I accepted that fact. All right. So, why does this matter? Well, when it comes to rational functions, typically when you see a rational function, it'll look like something like 1 over x. All right? The problem is that what cannot happen in the denominator? X cannot equal what? 0. So in this case, x cannot equal 0. And the reason is, if we do that, it'll be undefined. So very quickly, let's just kind of review. Domain for each given function. So first function is quadratic. What's always the domain for a quadratic? All real numbers. What about this next one? It's a cube root. All real numbers. All right, C, we got to do some legwork, so think carefully. How do I find it first off? Set x minus 5 equal to 0, or x minus 5, x plus 5, sorry, is greater than or equal to 0. Solve. X is greater than or equal to -5. So it'd be -5 to infinity. What about the last one? So you would set 5x minus 4 greater than or equal to 0. This would be 5x greater than 4. So x has to be greater than 4 over 5. All right. And again, the errors on your calculator lead to domain restrictions since the domain represents all defined x values in a function. Keyword defined. All right. If it's undefined at that x value, meaning that it has a corresponding y value. So, what does defined mean? Defined means it has a y value. All right. If you input the x, you'll get a y out of it. All right. So, let's look at some new examples. So, here's what I want you guys to do. Open up Desmos on your Chromebooks and put in that first function. See what you get. So, yeah. So just that first function. We technically already did, but I actually want you guys to see what it looks like. No, you don't need to type in f of x. You can just type in y equals. Guys, shh. So I know it's going to take you a minute to get your computers out, but when you type in this graph, what does it look like is going on? So we already said that for this function, we cannot have an x value where? When x is not equal to 0. So in other words, the y-axis. All right, when x is equal to 0, we're on the y-axis. What's going on with our graph there? Does it ever look like it's going to touch? No. So even though if we get like really, really close to it, watch this. So it looks like it's touching right here. Well, if I zoom in a lot, there's still space there. All right. Let's say I went all the way up to like 150 or 250. I zoom in a whole lot, still space there. All right. It's never going to cross that y-axis at all. So it's actually a physical line where it cannot cross. And we'll talk about what that's called in a second. But if I wanted to state the domain, first off, we know x cannot equal 0. So how would I write out the full domain in interval notation? It's not all real numbers. So it'd be negative infinity to where? 0. Now, do I use a bracket or parenthesis for that? No. Parenthesis, because what does a bracket mean? Defined. All right. Then we hit a union symbol. We pick back up at 0. And we go to infinity. Now, you may be wondering, well, why can't we just say from negative infinity to positive infinity? It's because it doesn't exist at 0. We're saying here that x can absolutely, in 1,000 years, cannot equal 0. Boys, what are you doing?
He's saying it equals 0 or it touches 0.
Nope.
Yeah, it's okay.
Show the class.
All right. Try the next one. See what happens. So the next one, where does it look like it doesn't, what x value does it look like it's not going to cross at? So if I type it in, 1 over 3x minus 4. Zoom in just a little bit. What number does it look like it's not going to cross at? What x value? So 4/3. All right. So in other words, it's pretty close to 1, but it's a little past it, but it's not quite halfway there to 2. All right. How do you think you know it would be 4/3 for sure?
4 divided by 3x is 4 divided by 34.
So guys, what's the absolute thing our denominator cannot equal? 0. So how do you think I would find the one number that it cannot equal to? Set your denominator equal to 0 and solve for it. And we're actually going to put the slash through so we know it's not equal to that. So this would be 3x cannot equal 4. So x cannot equal 4/3. So that means our domain would be what?
No bracket. Union. 4/3.
Good. Now, these values that we're finding, these are known as what we call excluded values or your restricted domain. So what excluded values means is exactly what it sounds like. It's excluded from the graph. There's only one x value in that entire graph that makes it cannot be all real numbers. All right? It's just that one number, that one little baby number that makes our domain not all real numbers. All right? That's why we call it excluded values.
Does it matter if you put like 4/3 to infinity, like before negative infinity and 4/3?
You usually write domain in numerical order. So from lowest to highest. So and to answer your question, yeah, it does matter. So whenever I write domain in interval notation, I just think about it on a number line, like what would come first to the left, then next, and so on and so forth. All right, the last one. If you graph that, what value does it look like your graph is not going to cross at?
-7.
It will look like it's not going to cross at -7, which if we just set our denominator to be not equal to 0, subtract the 7 over, they would not be able to reach -7. So our domain would be from -infinity to -7, then from -7 to infinity. So guys, what the domain is actually representing, it's representing the two different pieces of the graph. So do you see how the graph's in two different pieces? All right. The first part of the domain, so the -infinity to that number, represents this piece right here. All right, that's what this piece is represented by in the domain. Then the second piece from that number to infinity is represented right here. All right, it's this piece. So that's why we have to separate the two domains because it's representing two different pieces of the graph. So another way to ask this question is what values of x make the function undefined? So again, all you got to do is set the denominator equal to 0 and solve for x. All right.
Maybe not equal to 0.
Yeah, not equal to 0, equal to 0. It's pretty much the same thing, concept. It just can't be equal to 0. All right. So let's go back to looking at 1 over x. This is actually known as an inverse graph. So a rational graph is also known as an inverse graph. And 1 over x is actually the parent function of most rationals. So, remind me again what parent function means? The original. All right, so if we do any function transformations, it's going to base around this graph. So, we already know what the domain is because we found it already. So, what was my domain again? Right, so it would be this. So another way you could say this is all real numbers except x cannot equal 0. Because literally every other real number is represented there except 0. All right. Now, we'll come back to range in a minute, but let's look at how we would graph this. First off, we want to represent that it's not going to cross at 0. So what I'm going to do is I'm going to draw a dotted vertical line through when x is equal to 0. So in other words, it's going to go along the y-axis. This represents x equals 0, which math 1 concept, we know that x is equal to some number, that's a vertical line. Now, the way you would make a table is I would just get some numbers that are less than 0 and some numbers that are greater than 0, because at 0 it's undefined. All right, so we're going to get 2 above and 2 below. So I'm just going to do easy. So -1, -2, and 1, 2. So if I plug in -2 into my function, what would I get? So -1/2. If I plug -1 in there, what do I get? -1. If I plug 1 in there, 1. What about 2? 1/2. So it goes from -1 to -1, -2 and 1/2. All right. Now, let me ask you this. If I picked, say, -3, so I go one step higher, what would you get? -1/3. So here's my question to you. Is there ever going to be a point when your y value is equal to 0? No. Why do you think that is?
No matter how much you can divide the number, it's not going to be
Right. We could plug in 1,000,000 for x. It would just be 1 over 1,000,000. All right. So it'd be like an infinitesimally small fraction. So the left side of the graph would look like this. The right side, same thing. 1, 1, 2, 1/2. 3 would also be 1/3. So our graph would look like this. So on top of that, our graph doesn't only not cross at x equals 0, it also doesn't cross at y equals 0 either. So it also doesn't cross at y equals 0 either. So I'm going to draw a horizontal line on the x-axis. So what do you think my range would be? What's the only value in the range that does all real numbers except 0? So since y cannot equal 0, so it's all real except y cannot equal 0, that means we would write it the exact same way we did the domain. Now, these two lines that I just came up with, these are what we call asymptotes. All right, and all an asymptote is a line where your function is undefined. So if you have x equals some number, that's what we call your vertical asymptote. If you have y equals some number, that's what we call your horizontal asymptote. And you write it as an equation of a line. So it's not just going to be some number. You got to say either x equals some number or y equals some number. Why? Well, if I just say where are the asymptotes at, if you just tell me two different numbers, but you don't put x or y equals, I have no clue where that is on a graph. All right, so in this case, we would say our vertical asymptote is at x equals 0. Our horizontal asymptote is at y equals 0 for this specific graph. All right. So the graph y equals a over x minus h plus k. This is the general form of a rational function. So very similar to when we did a times the square root of x minus h plus k, same thing. All right. Where y equals k over x, where h is horizontally and k units vertically. That's the translation. All right, so the vertical asymptote is always going to be x minus h equal to 0. So if you solve for h, all right, so in other words, it would be when h is equal to 0. All right. Now, the horizontal asymptote. Now, in Math 3, you will learn all these different tricks for horizontal asymptote, how to find it. But typically, with a horizontal asymptote, for right now, it's basically whatever your k value is. All right. So if we look up at the original, our k value is 0. All right. But for horizontal asymptote, it'll be y is equal to our k value. Now, that's because we are dealing with very, very basic rational functions, because you're not going to deal with more advanced ones till you get to Math 3. So for right now, all it's saying is that if we move the function upwards k units or downwards k units, the horizontal asymptote moves with it. And all it tells us is how far the graph has been stretched from, or the function, dash graph, been stretched from the asymptote. So that's what A tells us. And we can use it to help us find out the corner points to start our branches. So if we look back up here, what it means by corner points is these points right here. It's typically the only point on the graph where it's like a solid whole number. It's not a fraction. All right. So those are what we call our corner points. And then after that, all we do is just kind of draw them along our asymptotes. So let's look at these right here. So while we do this, we're going to think about the fact that our general form is a over x minus 4 plus 3. Sorry, x minus h plus k. I don't know why I wrote that. All right, so this is what we're going to think about. So we're going to find our two asymptotes first, because that's going to give us an idea of where our graph's going to be. So vertical asymptote. So I'm just going to call this my VA. How do I find it? So what did it say up here that I need to do? Yep. That should be x is equal to h. Good lord. So it says x minus h is equal to what? 0. And that's exactly what we're going to do. We're going to take that, set it equal to 0, and solve. So what? So x is equal to what? 4. So that's our vertical asymptote. So if I want to go ahead and draw it over here, I would go to when x is 4 and draw a dotted vertical line. Horizontal asymptote. What I say your horizontal asymptote is always going to be? Your k value. And what's my k value? Positive 3. So it'd be y is equal to 3. So I'm going to go to where y is 3, and I'm going to draw a vertical line. Not vertical, horizontal line. Now, I then am going to find my corner points. And that's going to be based off of your a value. So just like how I said you want to find like your perfect cubes, you want to find what value of x would make it so if you evaluate this fraction, you would get 1 or negative 1. Why is that? Because if you look at the parent function, our corner values for x are at negative 1 and 1. All right. So if I want the fraction to be equal to 1, all right, that means I have to get what in the denominator? So in other words, I want 2 over x minus 4 to equal 1 when I evaluate it. So what value would this have to be equal to? 2. So in other words, we're finding what value of x gives us 2 in the denominator. So that when we do 2 divided by 2, it gives us 1. And that would be 6. So x would have to be equal to 6 for that to happen. So that's the first part of my corner point. Now, how do I get the y value? You just plug it back into your function. So all we would do is plug in 6. So that would be 6 minus 4, 2. 2 over 2 is 1. What's 1 plus 3? 4. So our first corner point is at the point 6, 4. So all you do is just plug it back into the original. Yeah. So that's one corner point. So I'm going to do that right here. So I wanted this to be equal to 1. All right, just the fraction part. So I knew the denominator had to be 2 because 2 divided by 2 is 1. So that'll be x minus 4. So if you set x minus 4 equal to 2, x has to be equal to 6. Does that make sense? All I did was plug it back into the original function. So I did 2 over 6 minus 4 plus 3. And that gave me 4 if you evaluate it. Because you have 1 plus 3. All right. Now, there's also another positive corner point that I can get. So that's just one corner point, but there's another one within the positive realm. It's based off of your A value as well. So if I look at my A value, all right, what's my A value? 2. So what number could I divide 2 by besides itself that would give me a non-fraction? 1. So if I do 2 divided by 1, I can also get another corner. So 2 divided by 1 would give me 2. So in other words, if I want 2x minus 4 to equal 2, I want this to be equal to 1. So what value of x would give me that? 5. So if x is equal to 5, that would give me a denominator of 1, so it would be 2. So in other words, if I plugged it in up here, I would have 2 over 5 minus 4 plus 3. So that would be 2 plus 3, which is what? 5. So another corner point would be 5, 5. So right here. So not only do you want to find the point that will give you 1 after you evaluate the fraction, you also want to find the point that will give you whatever your A value is. All right? Or the x value that give you whatever your A value is. So, in other words, you want it to be equal to 1 or negative 1, or A or negative A. All right? So we found the positive versions. Let's find the negative versions. So, what if I did 2 over x minus 4 and I want to equal to negative 1? What value or what should my denominator be equal to?
2.
So it needs to be equal to negative 2. So x would have to be equal to 2 to get negative 2. So if we get x equal to negative, not negative 2, x is equal to 2. Meaning, if I did 2 over 2 minus 4 plus 3, this would be 2 over negative 2 plus 3. So that would be negative 1 plus 3, which is equal to what? Which is equal to 2. So another corner point is 2, 2. So 2, 2. No, we want it to be equal to negative 2 in the denominator. But these are actually our x and y values. All right. Now, if our A value is 2, what's the negative version of it? So what's the negative version of 2? Negative 2. So now we want 2 over x minus 4 to equal negative 2. So that means our denominator should equal what? 2 divided by what number will give you negative 2? Negative 1. So what value of x would give me negative 1 if I evaluated it? 3. So x has to be equal to 3. So if I do 2 over 3 minus 4 plus 3, that'll give me 2 over negative 1 plus 3, which is equal to what? So that'll be negative 2 plus 3, which is what? 1. So my other corner is the point 3, 1. Now, why does that help us? Well, now we get a general idea of what our graph's going to look like. So we want to get really close to our horizontal asymptote, curve at our corner points, and then head on downwards, getting super duper close to our vertical asymptote. And we're going to do the same thing on the other side. We're going to start high with our vertical asymptote, turn at our corners, and then continue to go, but never crossing the horizontal. So that's what our graph would look like. Now, domain and range is really easy because it's just based off of your horizontal and vertical asymptote. So my domain would be what? So based off of our vertical and horizontal asymptote, domain would be using which asymptote? The vertical asymptote, because it has x equals. So how would I write my domain? So all real numbers except x equals 4, or you could write it as negative infinity to 4 union 4 to infinity. What about the range? Good. All right, any questions? All right. So let's do another one now. Okay, first off, asymptotes, vertical and horizontal. Vertical asymptote is always your what value? H value. Well, what's my H value? Not 1, -1. So if you forget that, just get in the habit of setting your denominator equal to 0 and solving. So your vertical asymptote is at -1. What's always your horizontal asymptote? K. What's my K value? -4. So if I graph the asymptotes only, I have a vertical line at -1, horizontal line at -4. All right. Now, corner points, let's just focus on our A values only. So my A value is what? -3. So I want the A value itself or the negative version of the A value. That's what I want that entire function to equal. So in other words, I'm shooting for -3 and what? +3 in that fraction. So let's say I want -3 first. So I want -3, x plus 1 is equal to -3. I don't care about the -4 right now because we're only finding the x value. What do I need my denominator to equal to? We need to equal to 1 so that -3 divided by 1 is -3. So what value of x would give me 1 in the denominator? 0. So x has to be equal to 0. What about y? Because we want it to be the a value. So you want either the a value or the negative version of the a value, or the opposite version. So we were going to shoot for 3 and -3. So now we're going to find the y. So -3 over 1 plus 1 minus 4, or 0 plus 1, sorry. Jump the gun there. So that'll be -3 over 1, which is -3. What's -3 minus 4? negative 7. So that's what's equal to y. So one of my corner points is at the point 0, negative 7, which I'm going to graph. So 0, negative 7. Yes?
How did you know to set it to -1 and 1? Like, we're all confused on how, like, you.
So how I know what to set the denominator to? If I'm shooting for the entire fraction to be negative 3, so just ignore the x plus 1 for a second. Let's just say I had negative 3 over x is equal to negative 3. What does x have to be? No, you just grab it where it goes. So like where it would go on the graph. Oh, yeah. I graphed it wrong. I'll fix it in a second. I graphed the opposite. I graphed the x-intercept to the y-intercept. My bad. Okay, guys, listen. So, think about it this way. If I have negative 3 over x, what would give me negative 3? 1. So that's why if I have negative 3 over x plus 1, and I still want to be equal to negative 3, that means I need the denominator for x plus 1 to equal 1. So that when I find the x value and I evaluate it, I would get negative 3 over 1. That's what I mean by that.
So you want the denominator to equal to 1.
Right.
But then you're also trying to make it -3.
Because negative 3 over 1 is equal to negative 3. So ignore this for a second and ignore this. I'm just trying to figure out the x value that would give me negative 3 if I evaluate. Yes?
And why is it not clear that's equal to -1?
Because now we're going to find the negative version of that. So now the next step is I'm going to want this version to equal to not 1, positive 3.
Why would you put that?
Because we want to find our corner points. So one of our corner points would give us something in here, and the other one would give us something here. All right. So in other words, it'll give us the positive part of the domain, the negative part of the domain. So that's why you base it around the a value.
So are we gonna switch to a value from negative to positive?
That's our next step. So if a, that's why you focus on your a value. A is equal to negative 3. Our corners, we want our corners, if we set our function equal to our a value or negative 3 and equal to its opposite, so 3. And that's where we're finding the x values.
So like when you switch it to a positive 3, you would make the x plus 1 equal to negative 1. So that would just like still have to.
Does that make more sense now?
Yeah.
And again, guys, the reason that like the point itself is not at negative 3 or 3 is because of that -4. Right now, I'm just focusing on the fractional part only. All right, so we're focusing on the division part. Okay? So, I screwed up that corner point, so give me a second to fix it. So that should be at the point 0, negative 7, so right here. All right. Now, we need the other to equal our opposite version of our a value. So that would be a positive a, because a negative times a negative is a positive. So we want the fractional part, so negative 3 plus 1, or over x plus 1, equal to positive 3. So that means that we want our denominator to equal what in order for that to happen? Negative 1. Because if we divide negative 3 divided by negative 1 would give us 3. So what x value would give us -1? -2. Now, since we found the x value that works, now we need the y value. So the y value is when we use the whole function. So we get y is equal to -3 over -2 minus 1 minus 4. So that's going to be the same thing as 3 minus 4, which is what? -1. So our other corner is at -2, -1. So right here. So this gives us an idea what our graph looks like. So in other words, we start at the horizontal asymptote and we want to go and curve so that goes through the corner and then get really, really close to the vertical asymptote. And we want the same thing on the other side, but we're going to start backwards. So we're going to start with the vertical, start really, really close to the vertical, but slightly turn until we hit the corner. And we're going to keep turning until we get to the horizontal asymptote, and then we're going to kind of level off. So I found 4 originally just to give you a better idea what the graph looked like, but in reality, you only need to find 2 of them. So I gave you some options. You either want your corners to, or you either want your fraction when you evaluate your fraction part of the function to be either 1 or -1, or the a value in its opposite version. Either one of those will give you a nice corner. Yes.
So like if you're finding the y value after you find x, you add
The k value, yes. Yeah. So remember what I said yesterday about like the square root stuff? We all had the question yesterday about why we were only setting the under the radical part equal to 0. We're finding the domain stuff. Same thing. The reason I'm only focusing on the fraction part is that the fraction part is only affecting the x. The k value does not affect the x at all. It affects the y. All right. So that's why I'm focusing on the fraction, because the fraction, or the denominator specifically, that's like the bracket, or it's the under the radical, or it's the parentheses. That's the only part that's affecting my x value. All right. That's what kind of controls what happened with this fraction. Because whatever I plug in for x, that controls when I get to that fraction. So then when I do subtract that 4 at the end to get my y, then the x value is taken care of. All right. So in other words, if I was like doing x plus 3 is equal to 0, or let's say x plus 3 is equal to 4, we know x is going to equal 1. All right. So it's the same thing. It changes. So if we want x to originally be equal to 4, but then x plus 3 we want to be equal to 4. The actual value of x changes. Because remember, x just represents a value. But our outputs are exactly the same. All right, so that's why we only focus on the fractional part, because we only care about what's happening to the x value. All right, the y comes into play when we need the other part of the point, and that's when you put it into the whole function. Does that kind of make more sense? And I know this is a pain in the butt, and I'm sorry, but it's just, rationals are just that way. Like, it's a weird function to begin with, so it's a weird concept to wrap your head around. So my suggestion, when you're trying to find your corner values, just shoot for whatever the a value is and then the opposite version of it. Now, domain and range, again, you'll just take your vertical, horizontal asymptotes. So it would be from -infinity to -1, -1 to infinity, and then -infinity to -4, -4 to infinity. All right, so I know it says for this to you try, but in kind of the spirit of the class, and since I know y'all are a little bit confused, let's just talk through it together. So I'm not going to say anything. Y'all are going to walk me through it. Okay? So we're doing robot, Miss Murphy. I cannot do anything until you tell me what to do. So first off, what do we start by finding? So we need the vertical and horizontal asymptotes. All right? Someone lead me from there. Mm-hmm. So x would equal what? So what is that? Good. Now what do I do?
Just K.
Mm-hmm. Which is?
So
Good. What do I do now? Where? What kind of lines? What kind of lines? So at x equals 5, what kind of line? Vertical. So guys, what you're doing is that you're going to pretend like you're talking to a robot who has no clue what you're talking about until you actually tell them what you mean. What about the horizontal? I'm drawing it at 8. Now what do I do? So what am I shooting for now? Okay, so we're trying to find corner. And what am I shooting for?
Are you shooting for 7? Or do you want it to equal?
Maybe over x minus 5 equals -1.
Okay, so first I want -1 over x minus 5 equal to -1. And why am I doing that? Because that's my a value. All right, so what do I want? So I then want -1 over x minus 5 equal to, what's the opposite? 1. So now what do I do? So what do I want that to equal to? 1 to equal to 1. So I have -1 over 1. So what does x have to equal to? 6. Then what do I do? Into the original. So I have -1 over 6 minus 5 plus 7. So that would be -1 plus 7, which is 6. So that's my y. So my first corner point's at 6, 6. So 6, 6. Okay, now what do I do? Okay, so then what about that? We want x to equal -1, or not x equal -1, x minus 5 to equal -1. X would equal 4. Now what do I do? Plug it back into the original. So I get -1 over 4 minus 5 plus 7. So that would be 1 plus 7, which is 8. So that's my other corner point. So it's at 4, 8. Now what do I do? How? So I start at the horizontal and then slowly rise till I hit the corner, and then I go as close as possible to the vertical. What about the other side? So the same thing, so I start over here.
Where's your cursor?
So I start the vertical. Well, it doesn't really matter, but yeah.
Since we're kind of robot. Actually, no.
Okay, so we're gonna, well, not quite done yet. Domain range. All real numbers except x cannot equal 5. If I were that interval notation, what would it be? So negative infinity, 5, union, 5, infinity. Range? Yep, for all real numbers except x cannot or y cannot equal 7. Okay. So we're going to stop here for today. For homework, I want you guys to do page 39, but just number 3. So those two graphs. If there's no k value, it's 0. Actually, do all of page. Nah, just do number 3. Just do number 3. So just do number 3 on page 39. So just those two problems. You can probably knock them out before class ends because you have about 10 minutes. So just number 3 on page 39. So that's those two graphing. Now, listen up. So, tomorrow, because we're going to start your test on Monday. So tomorrow we're going to finish up the last little bit, 5.7. We're going to review, and me and Miss Mel, we decided we're not going to do 5.8. So that means that in your journal, you do not need to do the 5.8 section. So you do not need to make a one-pager for 5.8. All right? So you can mark that out on your journal page if you want, but we're not going to do 5.8. We may do that as a mini lesson later, but not for time's sake because we want to get this done before Thanksgiving. We're not going to do 5.8. Yes, yes. I'm going to give you guys, so the last little part of 5.7 is quick. And then, so we'll start that with class tomorrow, then the rest of the time we're going to review. And I will give you a review packet tomorrow.